In our previous lecture, we saw that a function is a rule that assigns a unique number to every element in a specified set, which is known as a domain. So in other words, for every input that walks in, a unique number is assigned to that input based on some sort of rule. Now, in today's lecture, we'll look at something called functional notation. So a function may be pictured as a machine. So we can think of a function at one level as follows. So here is the function f. So here's the function. And this machine takes inputs, so we'll assign a variable to the input, so we'll call that x, so this would be the input. Something goes on in the box. Some rule is applied that can uniquely specify an output for whatever input happens to walk in. One of the examples we saw in the last consisted the age of students in a classroom. So the students in the classroom consisted of the domain, and any student who walks in, their age would walk out. So there's something perhaps complicated, perhaps simple happening in this box, but whatever it is, a unique number y is assigned to that number x that walks in. So the number x walks in, the function looks at the number x, figures something out, and says, okay, your age is 22, your age is 19, or whatever. Or, you know, a number could walk in. Number 5 walks in, the function x says, okay, number 5. Let's do a computation, and the output is 26.35. So 26.35 was assigned to the number 5 based on some rule. And so we're not going to worry too much about what the rule is. The rule is happening in the box. So right now we're just going to focus a little bit on the notation. So the notation here is we say that y is equal to f of x. So x is the input, but f of x is the function acting on x. So this would be the function f acting on x. So f of x is the output. Okay, so f is the name of the function, and then f of x is the output, which we might also call y. So by saying y equals f of x, we're saying we are assigning the variable y to represent the output, because the output is always f of x. Here's an example. F of x equals sine of x. So for the sine function, x is the input, and sine of x would be the output. That's an example of a function. Whatever number you type in, once you press a sine, a unique number comes out. So we would say f of x is equal to sine of x. So f of x works in a very similar way, though we might get something different. So let's consider a function f of x is equal to 3x squared plus 7. So this is a definition of a function. This is an example of a function given by an equation. And let's compute the output for a number of inputs just to see how the notation works. So suppose our input is 0. So we want to compute f of 0. In other words, we want to say, well, what number was assigned to the number 0? 0 walks in, what number walks out? Well, to do this, we just take 0 and replace x with 0 wherever we see an x in this formula. So it becomes 3 times 0 squared plus 7, and that's just equal to 7. So f of 0 is equal to 7. Let's do it again with 1. So what is f of 1? So if the number 1 is the input, what is the output? Well, f of 1 would be 3 times 1 squared plus 7, so that's just equal to 10. So f of 1 is equal to 10. Similarly, f of 2 is equal to 3 times 2 squared plus 7. 2 squared is 4. 4 times 3 is 12. 12 plus 7, 19. And we can continue this way. F of 3 is 3 times 3 squared plus 7. Well, 3 times 3 squared is 3 cubed, which is 27, plus 7, okay, 27 plus 7 is 34, like that. So any number that walks in, we can compute the number that comes out. What about f of t? Well, we do the same thing. We just look for the x in the equation and replace it with t. So here, if f of x is 3x squared plus 7, then f of t is going to be 3t squared plus 7. Let's see how it works. What about f of x plus h? So this is something that we'll see is very important to understand this notation right here, because we'll see it when we discuss and define the meaning of a derivative. So f of x plus h, it's the same game. We just, since this is f of x is equal to 3x squared plus 7. To evaluate f at any value, we just take that value and replace x with that value. So if we want to evaluate this function at x plus h, we just replace x with x plus h. So it's just 3 times x plus h squared plus 7 like that. Now I can expand this and I would get 3 times x squared plus 2xh plus h squared and then plus 7, or 3x squared plus 6xh plus 3h squared plus 7. Now I expanded that for a reason. I want to show you how it's different from 3x plus h. So if we do f of x plus h. So if we say f of x, close the parentheses, and then say plus h, it's very different, because the difference between these two is as follows. This one, the top one, we're taking x plus h as an input and inserting it into the formula and seeing what we get. And we got 3x squared plus 6xh plus 3h squared plus 7. In the second case, we're just taking f of x, so we're taking 3x squared plus 7. So here I just write 3x squared plus 7. That's the f of x. And then I'm adding h to it, so then plus h. So notice that f of x plus h, all in the parentheses, versus f of x plus h, where the plus h occurs outside of the parentheses, give two very different results. Right? So whatever's inside the parentheses, that's what you take and just replace x with the stuff in the parentheses. And then if something's outside of the parentheses, you just use standard algebraic manipulations. Now, we have all of these values. So we said f of 0 was 7, f of 1 was 10, f of 2 was 19, f of 3 was 34. So we can take a plane, an xy plane, and actually graph these. So we can graph y as a function of x. So for example, x is equal to 0, the output was 7, so we'll call that 7. So I guess this should be about 14, should be about 21. So 1, 2, 3. So when x is equal to 1, we got 10, which might be about here. When x is equal to 2, we got 19. X is equal to 3, we got 34. So if we fill this in, we get a parabola, and on the opposite side it's going to look the same. So this would be y is equal to f of x. So whenever we take a function and we take a continuum of inputs, so we look at all the x inputs and then compute the outputs and then arrange those values on the xy plane. So every point on this curve corresponds to an input-output pair. 1, 10. 1 is the input, 10 is the output. 2 is the input, 19 is the output. 3 is the input, 34 is the output. Right, we take a bunch of these pairs and put them all on the xy plane like this and form a curve. So this curve is called the graph of the function. So the graph of the function is a visual representation. And another way to think of the graph is it's a curve, and along this curve you have all the points in which it is true that y is equal to f of x. So if x is equal to 1, f of x is equal to 10. So at the point 110 on the xy plane, it is true that y is equal to f of x. So that point belongs on the graph, and so forth. So let's consider another function. So let's just not worry about its formula, but let's just draw a nice graph, and let's say y is equal to f of x. So this basically means that for any x value, like say this is x is equal to 5, you just look, you draw a vertical line and say, okay, we have x is equal to 5. What is the y value? The y value here might be 4. This means that f of 5 is equal to 4. So that's how graphs of functions work. Now, because a function associates a unique output to each of its inputs, whenever you have an input, which is an x value, you can only have a single output, which means the graph can only intersect this vertical line at one exact position. And that is called the vertical line test. So if you have a graph or a curve on a plane and you want to know whether or not it's a function, you can think about vertical lines. And your graph is a function only if each vertical line intersects the curve a single time. Because if a vertical line intersected the curve 2 times, it would not be a function, because that x value would have 2 outputs. So vertical line test means any vertical line can intersect your curve at most 1 time. I'll give you a non-example. So let's say we have an xy plane like this. I was going to go for a circle. Let's do something a little bit more interesting. So there's a curve. So is y a function of x? And the answer is no, because I can choose a vertical line, and then this vertical line intersects the curve at 2 points, which means that this x value, let's say it's -2, would have 2 outputs. But remember the definition of a function. Every input has a single output, right? So this fails the vertical line test, and therefore is not a function. So y is not a function of x.